All right, now we're going to talk about our first technique for solving these equations analytically, getting a closed form solution to a differential equation. So we'll start with a very easy example, then I'm going to do a very complicated example. Most of your homework is going to be kind of between the two. So hopefully that's fun and interesting for you. Remember our friend, y prime equals y. That's the very simple example, and it was so simple that we could even guess a solution. Y equals e to the x. I'm going to switch from t to x because we're going to use our Leibniz notation. So instead of y prime, we'll use dy by dx. Normally we have x here. You could use t, it's fine. Any two variables are fine. X maybe looks a little bit more comfortable for most of us. And there's this thing in calculus. It's kind of lurking in the background. Most of the time you want to think about dy by dx as just notation for the derivative of y with respect to x. But sometimes we're thinking about it as a very small change in y over a very small change in x, where these guys are both numbers. And in some calculus techniques, you can treat these as numbers. So what I'm going to do is I'm going to multiply both sides by dx, which, be very, very careful when you do this. Sometimes this is illegal. Sometimes you don't want to think about dx as a number, but here it's okay. So we always want both dy and dx in the numerator of different sides, so that we'll always be able to do that just by multiplying both sides by dx. And then I don't know how to integrate y with respect to x. So I don't want y over here. I'm going to get it over here. I'll divide both sides by y. dy over y equals dx. Now these are things that I know how to integrate. So then I just integrate both sides. And integrate that as normal. Integral of dy over y is the natural log of the absolute value of y. And the integral of dx is x, and we do have plus c's that we have to put somewhere. It's kind of a waste to put plus c's on both sides because I don't know what c is anyways. So if you just put it on one side, that's usually good. Okay, this is not a great solution. This is a lot better than what we started with since there's no derivatives. So we kind of know what we're looking at, but we want to get this into a y equals something format. Maybe we don't want an absolute value. Maybe we don't want this constant c, but we can't really do that unless we have an initial value problem. And then some domain things to note. I divided both sides by y. So here I'm really assuming that y is not 0. Let's just keep that in mind, because over here y can be 0. So maybe we can bring that back at some point. Okay, I don't like this natural log, so I'm going to rewrite this. Natural log means the power I put on e to get the absolute value of y is this guy, so I'm actually going to do that. The power I put on e to get the absolute value of y is x plus c. And now this is really e to the x times e to the c, where e to the c, I don't know what c is. C is some real number. So e to the c is just some other number. But remember, if we sketch a little graph of e to the c, all values of e to the c are positive. So I'm going to rewrite this. Absolute value of y is some constant k times e to the x, where k is greater than 0. Okay, but this is good. We can bring all our domain things back now. This is absolute value of y, meaning y could be positive or negative, and I get a positive thing over here. But instead of making the thing over here positive, I can just say y is anything, and k can be either positive or negative. And actually, I wanted to bring back y equals 0, which will happen when k equals 0. So really, I can take care of this, and the absolute value by just rewriting this as y equals k times e to the x, and k is any real number. This is notation for k is any real number, if you haven't seen this before. Okay, there's our solution to this differential equation. Remember our initial value problem, y prime equals y, and then y of 0 was 1. Okay, if you have an initial value problem, then we'll just sub that in, and then instead of a general solution, we can solve for k. So y of 0 is 1, so 1 for y equals k times e to the 0, 0 for x, right? That's 1. Okay, so k equals 1. Okay, so great. Our solution to the initial value problem is y equals e to the x. Okay, so there's general solution. There's solution to the initial value problem, which, yay, we were right. This guess is for the simplest version of that differential equation in this initial value problem. Another thing you can do is you can check your solution. So what are we looking for? The initial problem says, find me a function y in terms of x that satisfies this equation. And we actually found infinitely many, because k can be any real number. And we can check that they all work. So let's look at, this is the way I like to check things. We don't assume things are equal until we've checked them. Okay, so my left-hand side is y prime, and my right-hand side is y of the differential equation. And the solution I'm proposing is y equals k times e to the x. Let's check what the derivative of that is. So I need to take derivative with respect to x of k times e to the x. Constants don't matter, and then derivative of e to the x is just e to the x. So did that work? It did. I have left-hand side equals right-hand side. So my solution is good. All of these, for any value of k, satisfy the differential equation. And I'm actually going to do the complicated version in the next video.